Good morning, students. Welcome to the online classes in physics for standard ninth. Last class, I discussed with you the concept of momentum and Newton's second law of motion. And I had told that after discussing the second law, whose summary I have put in blue ink, after discussing that, we would discuss Newton's first law. So before discussing, let me summarize what we had discussed in Newton's second law. Before discussing Newton's second law, we had discussed about momentum, that momentum P of a body of mass m moving with some velocity v is given by the product of mass and velocity. And then we had discussed about Newton's second law. It states that the force is equal to the rate of change of momentum. So there are different forms of expressing Newton's second law mathematically. You can write it as mass times acceleration. Acceleration you can write as rate of change of velocity, that is v minus u by t. So m times v minus u by t. And if we multiply this becomes mv minus mu. mv is final momentum, mu is initial momentum. So we have pf minus pi by t. So this is change in momentum by time, that is nothing but rate of change of momentum. We shall discuss examples also afterwards. But today, let us now from this second law obtain the first law. Remember, this is the most important law that you should understand. If you have understood this, you will not have any problem in understanding this. Here F is what? F is the net means total or resultant, external unbalanced force. What is the meaning of balanced and unbalanced force? Very simple example you can take. Suppose you have a body resting on a floor. This body has some mass. One person pulls it towards right with force F. Another person also pulls it with same force F but in opposite direction. We say these two forces are in opposite direction and have equal value, so they will cancel, and therefore the body will neither move to right nor to left. Such a pair of forces is called as balanced forces. On the other hand, if we have a situation wherein there is a body and somebody pulls it with 10 Newton in one direction and 4 Newton in opposite direction, will these two forces balance each other? Of course no. Why no? Because 10 Newton is certainly greater than 4 Newton. So this body will move as if the net force F net is how much? 10 minus 4 Newton, that is 6 Newton. That's important thing to understand. If we have a 10 Newton force towards right and a 4 Newton force towards left, then their resultant value will be 10 minus 4. If they are in opposite direction, we have to subtract them. So these things you have read to some details in standard 8th. I hope you understand that. On the other hand, if we have a 10 Newton force and a 5 Newton force acting in same direction, can you tell me what will be the total force acting on this body? Because they are in same direction, they will help each other. Net force in this case will become F net is equal to 10 plus 5 Newton, that is 15 Newton. Is it clear, students? Okay. So with these ideas of balanced and unbalanced force and Newton's second law, let's try to proceed further. If the net external unbalanced force on a body, that is F, equals to 0. If F equals to 0, then what would happen? From this equation we see that mass times acceleration of the body will be 0. Is it clear? Now, if we have a body, all the bodies that you see around you, small, big, heavy, light, they have some mass. So mass will go that side. This implies we'll get A is equal to 0 upon mass, that will be 0. What does this mean? If A is equal to 0, the change in velocity will be 0. The rate of change of velocity. This is definition for acceleration. A is v minus u by t, that becomes 0. And if this becomes 0, then v minus u is equal to 0 into t, that is 0, and this implies v becomes equal to u. What is v? V is our final velocity. And what is u? U is our initial velocity. What does this mean? If final velocity is equal to initial velocity, this implies there is no change in velocity. This is the crux to understand Newton's first law, that if f is equal to 0, then there will be no change in velocity. Now this part we can divide into two subparts, part 1, part 2, or I'll write part A and B. If initially u is equal to 0, u is the initial velocity, suppose u is equal to 0, then what will be v, students? We have discussed v is equal to u, so then the final velocity v is also equal to 0, and the condition is given that external force is 0. So if f external is equal to 0 and initially the velocity was 0, then the final velocity will also be 0. This if you write in words, then what will state? U is equal to 0 means the body is at rest initially. V is equal to 0 means the body remains at rest finally. When there is no external force acting on that particular body. So what we can conclude from this, that if a body is at rest and no external unbalanced force acts on it, the total force, unbalanced force acting on it is how much? 0. And if this, then the body remains at rest. This is the first part for Newton's first law. Second part, if u is not equal to 0, let me take for simplicity to make you understand, let u is equal to 10 meters per second. Suppose initially the body was moving in a straight line. So it is moving in a straight line with a constant velocity of 10 meters per second. Such a motion is called as what? Such a motion is called as uniform motion along a straight path. Okay. And external force is how much? That is the starting point for our discussion. Here we assume that no external, the net external force on the body or the system is how much? 0. If f external is 0 and u is suppose 10 meters per second, then v is equal to u. So v remains how much? 10 meters per second. Okay. So if the body was having a constant velocity earlier, it will remain in that constant velocity forever if the external force is 0. In other words, we can restate that if the body is in uniform motion along a straight line and if the external force on the body is 0, then it continues or it remains in uniform motion. Is it clear, students? So here we have written two parts. This is part A and this is part B. If you combine both these parts, you will get the Newton's first law of motion. So according to Newton's first law of motion, if no external unbalanced force acts on a body, then it will not change its state of rest or of uniform motion. That means if initially it is at rest, it will remain at rest. And if it is initially in uniform motion along a straight line, it would continue to remain in the same uniform motion along the same straight line. This statement can be considered as the statement for Newton's first law of motion, and we could easily obtain this using Newton's second law. Is it clear, students? So if it is asked that obtain Newton's first law of motion from second law, you have to write these particular things. So we can now write the statement for Newton's first law. I have put it in my own words. I encourage you students that you should also try to put in your own words. No technical terms should be missing from your definition. I suggest you first go through the definitions as given in your textbooks or from other sources, then you can put them in your own words. I have used such a language which will be easy for you to understand. In absence of any external unbalanced force on a body, if initially the body is at rest, it remains at rest, part A. Okay? And if it is initially in uniform motion along a straight line, it continues to remain in uniform motion along the same straight line. So this is the statement of Newton's first law. What does it mean? If it is at rest, it does not want to come in motion, uniform motion, in absence of force. And if it is in uniform motion initially, it does not want to change its uniform motion. That means the body resists. So in other words, we can say all bodies, any body tends to resist any change in its state of rest or of uniform motion. Understand the meaning of this statement? All the bodies, they tend to resist. Resist means to oppose any change in their state of rest or in their state of uniform motion. What is the condition? Provided that net external force on the body is 0. This tendency of bodies to resist any change in their state of rest or motion is called as inertia. That is called as inertia. So the definition for inertia, for your reference, I have written, and this is the language of your NCERT textbook, students. The tendency of an undisturbed object. Undisturbed object means such an object on which the external forces are accumulating to 0. That means balanced forces are acting on it. So the tendency of an undisturbed object to stay at rest or to keep moving with same velocity is called as inertia. And because of this reason, Newton's first law of motion is called as law of inertia. So let me summarize. First law of motion says, in absence of external force, if a body is at rest, then it has an inertia. Inertia means it has a tendency to oppose any change in its state of rest. That means inertia of rest. And second part, if it is in uniform motion, it wants to remain in uniform motion. That means it has an inertia for motion. What is inertia? Inertia is the tendency of a body to remain in its initial state of rest or motion provided external force is 0. So this is the summary for Newton's first law of motion. So let's proceed further. Let us try to understand these concepts of Newton's first and second law with the help of an example. This is a very common example, students, which you must have done at your home also. You take a bowl or a glass like so, then cover that glass with a I don't have a cardboard, so I will use this. Anything you can use. You can use a cardboard, you can use a CD, whatsoever material. So I am using a CD, and over that you will put a coin. So I am taking a 10 rupees coin and I'll put it over the cardboard or CD. This is the arrangement. Okay. Now you see, concentrate on the coin. The coin is moving or it is at rest, so it is almost at rest with respect to us, of course. We say it has an inertia, that means it has a tendency to resist any change in its state of rest. It doesn't want to come in motion. So it is at rest, so it wants to remain at rest. Now what I would like to do, I would flip this, I would take this CD, I'll hold this CD and I'll apply a strong force to pull this CD away from the glass. And let's see, you must be knowing what happens next. But hold on, I have something more to discuss. So observe carefully. So this is the CD, I am holding it in my palm and then I'll pull it very hard. So you must have heard the sound sound related to the falling of coin into this glass tumbler. So you can see that coin, it enters into the glass. Now this explanation, you must be very much impatient, you must be knowing this particular explanation. So what explanation generally we receive or we get in the textbooks or from people, that yes, this coin has some mass, so it has some inertia, and when you pull this CD, because it was initially at rest, it wants to remain at rest. So when we pull this CD like this, it wants to remain at rest, so it remains at its position, but there is now no support for it, so it falls under the influence of gravity and gets into the tumbler. This explanation, I believe students, everybody amongst you can write yourself, so I suggest you to write this as an example. So this becomes an example for Newton's first law of motion to illustrate inertia of rest. So for Newton's first law, you can write the example for this one. We'll put a coin on the cardboard which is put over a glass. So this will be your assignment. Please write it yourself. But as I told, I want to discuss something more. Let's see the same example. We have the glass, we have the same CD or cardboard, and we have the same coin. Can you see the coin? I hope so. I'll perform the same thing now, but I will use comparatively lesser acceleration this time. I will reduce the acceleration of the CD and let's see what happens. You see this. Now if I ask you to write this explanation, what explanation can you give? What we expected, we removed the CD, the coin should have shown some inertia because it was at rest, it should remain at rest and it should fall in the tumbler, but that is not happening. What is happening is just opposite of what we had written in activity number 1. What is the explanation for this? And what is the explanation for this? So you must have noticed that in one case I am pulling it very hard and in second case I am pulling it gently. How does these two effects produce two different results? Now that is very important and that is what I would like to discuss. See students, in the first case I pull it with a greater force. That means the acceleration is of this cardboard or CD is more. If you apply more force, it will suffer greater acceleration. In second case, I had the same situation, but in this case I applied a smaller force, and because of that the acceleration of this cardboard was small. First of all, let me ask you a question, that in the second case, why did the coin move at all? Let me show it again. So I am asking you the reason for this. Why does the coin not fall into the tumbler? This can be explained on the basis of Newton's second law. When I moved this CD, this coin also moved. Question number 1. Initially the coin was at rest, but afterward is it at rest? No. That means there is some change in its velocity. Do you agree with this? I hope so. So here what did we observe? Please listen very carefully. Initial velocity of the coin, for coin, initial velocity was how much? 0. But its final velocity is not 0. That means there is some change in velocity for the coin. If there is change in velocity of the coin, that means there is some acceleration of coin. And if there is acceleration of coin, there must be force on coin. CD logic. Initially the coin was at rest, it moved, that means there is change in velocity, that means there is acceleration, that means there is force. Question: who is exerting this force and what kind of force is acting on the coin? You have to tell me the answer. Due to which force this coin is moving? So remember, this coin, see, this coin is in contact with this CD or the cardboard. So who is exerting this force? The CD is exerting the force. And what is that kind of force? That force is frictional force. Remember that. So when I am moving it slowly, there is force of friction between this coin and this surface of CD acting in that direction, and that frictional force actually leads this coin to move in that particular direction. It might look a bit surprising for you, but this is the correct answer. This coin moves because of friction. Generally we have an idea that friction opposes the motion. That is an incorrect statement. Friction always opposes relative motion. Actually, in this case, if you try to move this CD very fast, you will observe that the coin tends to move backward relative to the CD. So the frictional force on this coin is actually acting in that direction. Because of that friction force, it moves along with CD. That means it does not slip. Clear? This friction is what kind of friction? With respect to CD, this coin is not moving. That means it is at rest with respect to CD. At least we can say that. That means the friction is static in nature. Static friction you have read in standard 8, students, and you have also read that this static friction is self-adjustable and it has a maximum limit to which it can increase, and that value is called as limiting friction. This is this explanation for second part, that when you move this CD slowly, then the static friction between the CD and the coin exerts force. In the reverse sequence, we'll write the answer. So that question mark should be replaced by what? Static friction between the coin and the surface of CD or whatsoever material you are using. So what should be your answer? You can put in your own words like this. So when you move it slowly, the static friction between the coin and the cardboard exerts a force on the coin. Because of this force, the coin accelerates along with the cardboard. See, the cardboard is moving. Who is exerting force on the cardboard or the CD? My fingers. So the cardboard accelerates, and with the same acceleration, the coin also accelerates. Both of them are moving with same acceleration. Acceleration of the cardboard is because of the force which I have applied, and acceleration of the coin is because of the force which the cardboard has applied, that is frictional force on the coin. This frictional force, which is static in nature, is sufficient to produce that much acceleration on the coin. That's why they move together and it does not enter into the glass. In first case, when you move the CD very fast, the acceleration is large. To make this coin move along with CD, it has large acceleration, so large amount of force should be exerted on this coin. Frictional force, static friction between this coin and this CD cannot increase to that large value to produce this large acceleration. So in this case, what we can write? Here the static friction, ST for static and FR for friction. The static friction between same thing, coin and the surface, is not sufficient to produce this large acceleration on the coin as the acceleration of the cardboard produced due to the external applied force. So when you move it very fast, this cardboard or this paper or whatever material you have used accelerates at a great rate. The coin cannot accelerate at that great rate. Why? Because who is exerting the force on the coin? The static friction. And that static friction has some limitation. It is smaller force. It can produce a small value of acceleration, but it cannot produce that large acceleration as in the first case. So the coin fails to move with the cardboard. Suppose this is the coin, it fails to move with the cardboard. So it, because of its inertia, wants to remain. It allows the cardboard, okay, move, I can't accelerate this much. The friction between me and you is not sufficient. So I'll prefer staying here. So it prefers to stay there. Actually, slightly it must have moved, but then because the glass is quite big, a glass mouth is quite big, it lands somewhere inside the glass and enters into the glass. Is this clear? Other examples given in your textbook, like for example, the coins of a, in case of carom board. So if you have a pile of coins and with the striker you hit the bottommost coin quite hard, then it comes out and the remaining pile just settles down on the carom. These examples can also be stated for Newton's first law. So the first case was, the correct explanation for first law will be based on Newton's first law, and for second explanation you have to use second law. Where we have used second law here? Here we are using F is equal to ma. Clear? So I hope this explanation is clear. So both these parts are very interesting. You should be able to understand that. So please pause the video, understand this. Please perform the activity yourself and try to figure out the physics behind them. And both these explanations, students, please note down in your notebooks. And let me conclude today's discussion with the concluding remark regarding inertia and mass. Inertia, you have understood, students. Every body has a tendency to oppose or to resist any change in its state of rest or motion. But if that body is heavy, it will have more opposition. That means it has more inertia. So we say heavier bodies have greater inertia. On the other hand, lighter bodies have lesser inertia. That means I can conclude that mass of a body is a measure of its inertia. For example, suppose there is a football on the ground, and on the same ground we have, suppose there is a big stone. So this is football and this is a big stone. Both of them are initially at rest. So both of them have inertia. Which one will have greater inertia? This one. How will you know that it has greater inertia? Try to push them. Even with your finger, small finger, you can push this football. It will change its state of rest and it will come in motion. But to push this, you will have to apply larger force. And then if you try to do it so for a rock, you will fail to do so because it has large value of inertia, because it is very, very heavy. So that is the concluding remark. Mass, remember students, it is a measure of inertia. I'll give you some assignments. These assignments are from your NCERT textbook only. Try to answer them if possible. And if you find some doubts, we can discuss in our next class. See, we have not yet finished. We will discuss many examples and numericals based on Newton's first law and second law in the next class. So till then, goodbye students. Please revise these contents properly and try to read word by word of your NCERT textbook also. That will also help you in developing your knowledge based on these concepts. Okay students, thank you. Take care. Read well.